Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise where we're going to determine the convergence or divergence of the given infinite series. But the test that we should apply for each case is not provided to us, so we have a pool of available tests applicable for the given infinite series. So we're going to assess which test is more applicable for the given series out of the N-term test, p-series test, integral test, limit comparison test, and geometric series, telescoping series test, and the direct comparison test. So, in fact, telescoping series test is just showing that the given series is a telescoping series, so there's a special treatment to find the convergence of those series. Alright, so we have three different types of infinite series I picked for you, and let's get started.
Alright, let's start with part A. I want to use all of those tests for one of those examples, whether or not the tests are applicable for the given infinite series. So for part A, let's just think about, you can pause the video, in fact, you can think about this by yourself. So let's just try each test to see if I can apply the test to part A, okay? For example, let's start with Nth Term Test, okay? So can I apply the Nth Term Test to part A? And at this moment, you should remember that Nth Term Test is only applicable to prove the divergency of the given infinite series. So if I'm in the direction of proving it's divergent, okay, yeah, let's check if the Nth Term Test is available for us. But this doesn't look like a divergent series because it's 1 over 5 to the n plus 1. This looks like the series 1 over 5 to the n. So if you apply the Nth term test by taking the limit of the nth term, well, as you see that the top is always 1, the bottom is converging to infinity. So 1 over infinity is taking you to 0. When the limit of the nth term is 0, you can't conclude anything. Okay? If this limit was different from 0, yes, then I would just say the series is divergent. But that's not the case. So what that means is I cannot apply the Nth term test. Okay, I'm going to put a cross mark here. Okay. Can I apply the p-series test? Well, the answer is still no, because this is not a p-series to start with. P-series are of the form 1 over n to the p. Well, this is not 1 over n to the p, right? P is a given number, so this is not a p-series. So I can go ahead and conclude that, well, I can't apply the p-series test. Okay. Now the good question is, can you apply the integral test? Let's say like the conditions of the integral test are all good. Let's say, you can check it by yourself by pausing this video. But let's say like all the conditions are met. So now you have to ask this question to yourself. Am I able to integrate this function from, let's say, 1 to infinity? So do you know, in other words, how to integrate this function? So if the answer is no, don't use the integral test. Okay. So again, for you to be able to use or make use of the integral test, you should know how to integrate the nth term of the series. If you don't know anything about it, okay, don't do that. And this kind of integral is not easy to integrate to start with. Okay, so I would just say like, let's not apply this. Okay. Let's look at the geometric series. Is this a geometric series? Okay, geometric series are of the form some number a times r to the n. Okay. Well, I can't see that the given infinite series is of this form, right? Where is a and what is r here? So I can't see that it's a geometric series. So I'm going to go ahead and then put a crossbar, cross sign next to that. Okay. Is this a telescoping series? Well, the answer is still no, because telescoping series are written in terms of the differences of two fractions, right? And we generally use the partial fractions for those. if you remember the exercises that we went through for telescoping series. Okay, well, this is not a telescoping series for sure, so I can't really use the strategy of the telescoping series test. Okay, so I can't do that. So now we're back to limit comparison test and direct comparison test. Okay, well, okay, if there was no one here, what do you think that the series would look like? Because 1 in comparison to 5 to the n for large n is just nothing, right? It's very minor. Well, I can see that this series resembles to 1 over 5 to the n. Okay? So now it's up to your taste to use either direct comparison test or the limit comparison test. Okay? I can immediately use the direct comparison test because I know that 1 over 5 to the n plus 1 is always less than or equal to 1 over 5 to the n. Right? Because you're dividing by a bigger denominator on the left. Okay, so the series would satisfy the same type of inequality. And as I said, this series is a geometric series for r equals 1 over 5. Okay, so geometric series, right? R equals 1 over 5. It's convergent, okay? This series is convergent. So is this one, because, well, if this series is less than a convergent series, so this better be convergent, okay? So I can use the direct comparison right away to prove that this series is convergent. So yes, direct comparison test is applicable. I can tell you that the limit comparison test is applicable too. So now it's a good time for you to pause the video and apply the same strategy of choosing the second series to be the geometric series here, but this time using the limit comparison test. So that means you're going to look at, this is your homework. You can again pause the video and look at what's going on. Okay, so if this limit is finite, okay, then both series converge or diverge in the meantime, but since this series is convergent, right, geometric series is convergent, so this has to converge. I can tell you that this limit is 1, by the way. Okay, so 1 is a finite number. The limit comparison test says, like, since this is less than infinity, this is less than infinity, so both series convergent. I actually solved the problem, I'm sorry. All right.